In this chapter, we're going to calculate a lot of different confidence intervals for various population means or p-hat parameters. So our first one we're going to do here is we're going to use the formulas, and then I'll show you how to do it in Excel. So we're going to be constructing a 90% confidence interval for the population mean and interpreting the results. It told us that we have a sample of 48 days in a recent year, and they had a different mean price of 3.63, and the population standard deviation is 0.21. So the fact that it's the population standard deviation is important. That tells us we're going to be using the normal distribution. So our formula for our margin of error is going to be the z from our normal distribution that goes to our level of confidence times the population standard deviation divided by the square root of n. So here we're doing a 90% confidence interval, and so this comes from the bottom corner of our confidence our normal distribution table, and so it helps us be able to find it more easily. So that goes to a z of 1.645. Our standard deviation was given to us of 0.21, and then our square root of our sample size goes in the bottom. We have 48 different days that were sampled, so that goes in the bottom. So once you do the math to find the square root of 48, put it in the bottom, multiply it times 0.21 and times 1.645, you should get about 0.04986. That's a lot more decimals than we need. Our original thing, because we're talking monies, is only into 2 decimals, so we're going to round this to 5 cents. So this means our margin of error to be 90% confident is 5 cents. So now that we have the margin of error, we're going to add and subtract that from the mean. So our mean is $3.63. We subtract 5 cents and get $3.58. And we add, we add 5 cents to get $3.68. So that means with 90% confidence, we can say that the average price of gasoline during this time period, or in general, is between $3.58 and $3.68. Now we're going to do the same thing. The main difference is that now we want a 95% confidence interval. We still have a sample of 48 days with $3.63 as the average and 21 cents as the population standard deviation. So we're still going to be using that same formula that we had last time. The only difference is now that we're looking at a 95% confidence interval, that means our z becomes 1.96. The standard deviation is still 0.21 and our sample size is still 48. So for calculating that, we still do all of the same steps as before, but multiply times a different ZC, and we get 0.0594 if you round to all the different decimal places, or several decimal places. But this is money, so we're going to stop at 2 decimal places, so 6 cents. So now we do the same thing of subtracting that from our mean and adding it to our mean, and we get this for our range. So now we can be 95% sure that the price is between $3.57 and $3.69. So now we're going to look at comparing those two after we show how to do it in Excel. 95%. So now we'll look at how we calculated all of those things, but we're going to use Excel to do it this time. So it's going to help if we talk about our different parts of it. So we're going to need an alpha, we're going to need the standard deviation, and we're going to need the sample size. Those are the 3 parts for each one. So I'm going to insert a row up here. So we'll have question 1 first, and then we'll look at question 2. So alpha is 1 minus the confidence interval. So the first one had a confidence interval of 90, so that's an alpha of 0.1. And when I say 1 minus the confidence interval, I mean in decimal form. Whereas the second one went up to 0.95, so that's a smaller alpha. Both of them have a standard deviation of 21 cents and a sample size of 48. So those are going to be the same. So to get our margin of error, we're going to do confidence. Notice it's got several options. Norm is for using the normal distribution. So when you have the population standard deviation, that's what you'd use. T is for using the T distribution. So that would be if you were using the student T distribution, like we'll use in future problems. But right now we're using that one. And then our margin of error, it tells us it wants the alpha, it wants the standard deviation, and it wants the sample size. Put those together and it gives you your margin of error. So then to find our min and our max, I'm going to change to have the mean, min, and the max. So our mean here was $3.63. So our minimum, we take our mean, subtract out the margin of error, and then for the maximum you take the mean and you add the margin of error. And that gives us the exact same answers we had before. If you don't like seeing them in so many things like that, under number you can decrease your decimals so that you just have those 2 digits that we're rounding at. So I'll reproduce it. You could technically copy over to the right and it would fill in everything for this problem, but because it's new, a new method, I want to still show it step by step. So our first step is our alpha, which is that top one, and then a comma, and then our standard deviation, and then our sample size. And we see the same number we got before. We have the same mean as we did before. So it's our mean minus our margin, and our mean plus our margin. And again, I'm going to go under the number options and decrease to get that. So as we increased our confidence from 90 to 95%, we can see that our confidence range has increased as well, right? Our margin got bigger and therefore the whole interval itself got bigger as well. So as you increase your margin of, or your confidence, you increase your margin of error and therefore increase the confidence interval as well. Now for this one, we're trying to find the population mean cost for replacing a car's transmission. And we've done a study, found that there's out of 50 replacement costs, the average was 2,650. The population standard deviation, you know to be 425, and we want to construct a 95% confidence interval. There's our last number we'll need. So for a 95% confidence interval, that goes to a z of 1.96. So for our margin of error, it's our z times our standard deviation, 425, divided by the square root of our sample size. So again, we're using the normal distribution because we have the population standard deviation. If we had the sample instead, and we only knew what the sample standard deviation was, then we'd have to use a different one. So we're using that now. So once you calculate that and round to 2 decimal places, you get $117.80 for your margin of error. Then to be able to figure out what your confidence interval is, you take your mean and you subtract out the $117.80 and you get $2,532.20, and then you take the mean and you add $117.80 and you get $2,767.80. So that means with 95% confidence, we can say that the population mean is the price for replacing a transmission in a car is between $2,532.20 and $2,767.80. Again, I started off by saying we can be 95% certain that, because here the words mean something. It doesn't mean there's a 95% chance that the population mean is in here. It's a little bit more than that. And it has very specific wording for a very specific reason. For this one, we have pretty much the same situation, except that now we're looking at a sample size of 80. We still have the population standard deviation of 425, and we're constructing a 95% confidence interval. So this is still the same number. The only thing that's going to change in our margin of error calculation is the number in our sample size. So we're going to see what happens as our sample size changes. So this is our new formula that we'll calculate. It's our same z that we had before because we're still looking at a 95% confidence interval. Our standard deviation is still 425, but we're going to divide by the square root of 80 because our sample size has grown. And so we see now that our margin of error is $93. So it's gotten smaller than it did in the previous one because of that larger sample size. So now we do the same thing we did before. We subtract out the $93.13 and you add it to your sample mean. And so that's going to give us for our range $2,556.87 and $2,743.13. And again, that's we can be 95% confident that given these parameters, the average price to replace a transmission is between $2,556 and $2,743. So again, we have a similar setup. We're back to 50 different things in our sample, like in the first scenario. We still have the same mean, and we're still looking at a 95% confidence interval, but the population standard deviation has gone down to 375. So that means when calculating our error, we still need our 95% confidence interval z of 1.96. We multiply that times our standard deviation, which is still 300, or not still, it's now 375, and it's divided by the square root of 50. So once you calculate all that out, you get 103.94 for our standard, or our margin of error. So we take that, subtract out 103.94, and get 2,546.6, and then add it and get 2,753.94. So now 95% confident that the population average price of replacing a car's transmission is between $2,546 and $2,753. So again, in our comparison here, we're going to set it up in Excel so you can see how you could have answered them. So we're going to need our alpha, our standard deviation, and our sample size again. And we're going to compare question 4, question 5, and question 6. So for all of them, they were 95% confidence intervals, so that alpha is 0.05 for all three. The standard deviation for the first one was 425. Same goes for the second, but went down to 375 in question 6. The sample size was 50 in the first one, 80 in the next one, and then back down to 50. So we're going to find our margin of error and then use our mean to get our minimum and our maximum. So our mean for all of these was 22,650. So we'll go ahead and plug that in, and we're ready to start filling in using our formulas. So again, we're finding a confidence interval, and since we have the population standard deviation, we're using the normal distribution, so we're going to use confidence.norm. Our alpha is 0.05, our standard deviation is 425, and our sample size is 50. So with these, I'm doing a cell reference, but you could also just directly type the values in. It is up to you how you want to calculate them. And we get a very similar number we had to before. And so here I can drag it because of how I've set it up. You also could just type in each one. It depends on how you have it set up as well as what you feel comfortable doing. So then for our minimum, we take our mean, we subtract out our error, and then for the maximum, we take our mean and we subtract out our error. Oh, not subtract, excuse me, wondered why I got the same number. We add them. I'm going to, again, make these down to 2 decimal places because we're talking about money, and then fill them over. And it's going to use all the different ones. So like I can double click there and make sure it is doing what I think it's doing, and it is. And you should see very similar numbers to what you saw before. So now that they're all in one window, it's going to be easier to compare them. So the difference between question 4 and 5 was the sample size. It got bigger. And when the sample size got bigger, the margin of error got smaller, right? Because we were dividing by a bigger number. And so as your sample size gets bigger, as your sample size gets bigger, your margin of error gets smaller, and therefore your confidence interval gets tighter as well. If you were to plot these numbers on a number line, you would see that the minimum when you had a sample of 50 is lower than the minimum when you had a sample of 80. And the maximum is higher for a sample of 50 than for 80. So it covers a much wider range. So if you want a tighter confidence interval, one that's more narrow, then having a larger sample size would help you accomplish that. Okay? And then comparing this last one to the first one, what's difference between question 6 here and question 4 is the fact that our standard deviation went down. And when your standard deviation goes down, your margin of error is also falling. And so when that falls, our minimum and maximum are going to get closer together as well, so our confidence interval tightens. So another way to have a tighter confidence interval is to have a smaller population standard deviation. Seeing as you can't really control that, that's not really something you can change in how you're doing an experiment to try and have a tighter confidence interval. But the size of your sample is something that you can change if you wanted to have a tighter one. So for these questions, we need to determine the minimum sample size. So that formula is to use the critical value you find from the normal distribution times the standard deviation of the population divided by the margin of error all squared. So let's find our parts we need. So our 95% tells us what z we're going to end up using. It tells us we want to be within 1 unit, so that's going to be our margin of error, and the standard deviation is 4.8. So a 95% confidence interval translates to a z of 1.96 times our standard deviation of 4.8 divided by our margin of error of 1 all squared. And so that comes to 88.5106. But you can't survey a fraction of a person, and with minimum sample size, you're going to always round up no matter what. So here we're going to have an 89-person sample size. And again, and for these we round up because if you round down, then you have something below the minimum, and you can't go below the minimum. It's okay to be above it, but you can't go below it. So let's do it again, but now we want to be within 2 units. We're still going to be 95% confident, and we still have a standard deviation of 4.8. Again, this is a population standard deviation, which is why we're using the normal distributions z in our formula. If instead we had the sample standard deviation, we would need to use a different formula. So we plug in 1.96, we multiply it times 4.8, but now our margin of error is 2. And so once you multiply, divide, and then square that, that comes to 22.12 0.1276. But again, you can't have a fraction of a person, so we're going to round up. Yes, I realize 0.1 normally rounds down, but again, you can't go below 22.1276, and 22 is below that. So we have to round up to 23 being our sample size. So here we found that when our margin of error goes up, then that makes our sample size go down. So if we're willing to be further off or have a wider confidence interval, then you don't need to take as much of a sample size. We saw that in an earlier problem as well, but here it is in another way. In a random sample of 8 people, the mean commute time was 35, so that's in our sample, and the standard deviation was 7.2. Now this is for the sample, so that is S, not sigma. And then we're also assuming it's normally distributed, got a little typo there, with 95% confidence interval. So again, because it says in a sample, you find this to be the standard deviation. That means we can't use the normal, we're going to use the t-distribution. So the t-distribution looks a little like what you see over here on the right. So the first thing is this degrees of freedom. So for this one, well, for all of them, our degrees of freedom are n minus 1. N being our sample size. So that's 8 minus 1, or 7. So 7 is our degrees of freedom. There's also 3 different things you'll see here. We'll use the 1 and 2 tail in the next chapter, but for this one, we're just using the confidence. And we want to be 95% confident, so we use that. So we read over and get that 2.365 is the critical value we'll use in our margin of error. So now our margin of error is a very similar formula. The only difference is we have a t instead of a z because we have an s instead of a sigma. So that's 2.365 times s, which is 7.2, divided by the square root of our sample size, which is 8. If you do all of that, you get 6.0203. Since our mean is rounded to 1 decimal place, we'll do the same here, and we'll just call our margin of error 6. So we're going to subtract 6 to get 29.5, and we're going to add 6 to get 41.5. So we can be 95% confident that the mean average of commute time is between 29.5 minutes and 41.5 minutes for the whole population and not just for our sample. Now I'll show you how to use Excel when you have to use the t-distribution. So there's going to be a few things we need to know first. First is the degrees of freedom as well as the alpha. We're also going to need to know the standard deviation for our calculations. So our degrees of freedom is the sample size, which is, in this problem, 8 minus 1, so 7. The alpha is the level of confidence, which is 1 minus the confidence interval of 0.05, and the standard deviation is 7.2. So now, to get our margin of error, when you type confidence, you can see your options, but we're going to use t because we're using the t-distribution. And you can see the first thing it wants is the alpha, and then it wants the standard deviation, and then it wants the sample size. So it actually doesn't want that 7, so I'm going to just enter 8 because it can calculate for the degrees of freedom itself. So here we get that our margin of error is 6. Our mean was originally 35.5, so to get our minimum, we take our mean, subtract out that, and for our maximum, we use our mean and add the error. So again, if you want to see what I did for the standard error here, I just selected the alpha, which is 1 minus the level of confidence, and then the standard deviation, and then the sample size, not the degrees of freedom. This question has a similar setup. We've still got 8 people with an average of 35.5 minutes, but now our population, we know a population standard deviation. So we're actually not going to use this t-distribution at all because it tells us the population standard deviation. And so we're going to use that one. So we're back to our old version where we use ZC times sigma over the square root of n. And your ZC is 1.96, so that's using the table that we used earlier. And our standard deviation is now 9.3, and we're dividing by the square root of 8. So when you work out that calculation, you get 6.4446, right? And again, we'll round to 2 decimal places as 6.4. So for our mean, we're going to subtract 6.4 and get 29.1, and you're going to add 6.4 and get 41.9. So we have a different standard deviation than we did before, but also our critical value changed because we were using a normal instead of the t. And again, that's because we have the population. So you don't use the t distribution if you have the population standard deviation. When you have the sample, you do use the t distribution. So now we're going to use our confidence intervals to find the confidence interval of the population proportion. So that's back to similar to like our binomial distribution and all of that. So first we're going to have to find what's called our p-hat. That's how you pronounce that, p-hat. And that's just the predicted value for our proportion p. So for this one, to find our p-hat, it's the number of yeses or whatever we're looking for divided by the total number of options. So in this one, we had 396 yeses out of the 674 people. And so when you divide that out, that comes to approximately 0.588. But we also need our q-hat, which is the probability of the opposite of p-hat. So it's 1 minus p-hat. In this one, it's 1 minus 0.588. which is 0.412. So to get our margin of error, we're back to using the normal distribution because remember last chapter we did something where we showed that the binomial could be approximated using the normal distribution. That's where this is coming from. And so you take that and value and you multiply it times the square root of p-hat q-hat over n. And the reason this isn't just our simple like sigma over square root of n is because the standard deviation of a probability distribution like this one is this uses p-hat and q-hat in it. So it works out to this being our formula once you adjust for those differences in the distributions. Okay. So since we're doing a 90% confidence interval, that means we have a z of 1.645 from our table. At this point, I've just used it so many times that I wasn't even looking it up. But you'll still have access to it on a test or something, so you could. P-hat is what we just found to be 0.588. Q-hat is 0.412. And n is our sample size of 674. So once you multiply, divide, square root, and then multiply a little bit more, you get 0.03118 for your margin of error. I've been rounding to 3 decimal places, so I'll keep that up, and we get 0.031. So to get the confidence interval from the margin of error, we need to take the p-hat that was calculated, subtract out the value for our margin of error, and you get 0.557, and then we're going to add that number and get 0.619. So based on this, we can be 90% confident that of males between the ages of 18 and 64, roughly 55.7 to 61.9% say they have gone to the dentist in the last year. Now we're going to do the same thing, except we want to do a 95% confidence interval. So that means our p hat is just the same as it was before, of 0.588. Our q hat is still 0.412. The only thing that's changing is our z. It's now gone up. So if we want to find our margin of error, that's our z, which now that we're at a 95% confidence interval is 1.96. And then it's times p hat times q hat in a square root divided by 674, our entire population. Or not population, excuse me, the entirety of our sample. And so that comes to 0.03716. Or if we round to 3 decimal places, 0.037. So we see that our margin of error has gone up a little bit because our confidence level went up, just like it did in the previous sections. So we take our value of 0.588, subtract 0.037, and get 0.550. Excuse me, I was rounding incorrectly a little bit ago. So 0.551. And then add 0.037 and get 0.625. So now we can instead be 95% confident that between 55.1% and 62.5% of males between 18 and 64 in the United States went to the dentist last year. Define minimum sample size when you have this different type of like p-hat distribution. You have a different formula. So I'm going to write it in the bottom corner so it'll be easy to reference. So to get your minimum sample size, it's p-hat times q-hat times your critical value z divided by the margin of error you're seeking, all squared. So that p-hat and q-hat isn't squared, but the rest of it is. Okay. Now, when you don't know p-hat and q-hat, then you have to sort of maximize your minimum. So you want the biggest possible minimum sample size you could ever calculate, and that happens whenever p-hat is 0.5 and therefore q-hat is 0.5. So this comes from optimization rules. You could also just plug in a bunch of different p-hats and q-hats, and no matter the confidence interval and margin of error, these two are going to give the biggest possible minimum. So that's what we're going to have to use for this one when we don't have a preliminary estimate. So we've got those two in place of our p-hat and q-hat. Here we want to be how confident? We want to be 90% confident, so that's 1.645. And our margin of error, we want to be within 3%. So 3% in decimal form is 0.03. So that gives us that 0.03 in the bottom. So you would divide and then square, then multiply it times both 0.5s, and you get 751.673. Again, anytime you're calculating minimum sample size, no matter what the decimal is, you always round up. So we find that we need to survey 752 people if we're not sure what our sample size or what our preliminary p-hat and q-hat are. But in B, it says that we do have an estimate, and that estimate is 43%. So p-hat is 0.43, leaving q-hat to be 0.57 because q-hat is 1 minus p. So to find our minimum sample size, we'll now instead plug in the specific values that we have estimated for p and q. The rest of it's going to stay the same. And when you multiply and square and everything, you come out to 736.940. Again, rounding up because you can't survey a part of a person, that's 737 people. So when we have an estimate, we don't need to have as big of a sample as when we don't have an estimate. So having an estimate, having a p-hat estimate means a smaller sample is needed. because we're still going to be able to have the same confidence interval within the same margin of error in both of these scenarios. The only difference is we can ask 15 fewer people in the bottom scenario because we have an idea of what they are. And the further p hat and q hat are from 0.5, the even smaller from the other number this will become.